I would like the third speaker to show himself or herself for the next paper called Development of Methods for the Automatic Control of the Manipulator Drives of a Mobile Weeding Robot with a Parallel serial Structure. So do we have any one of the authors available here to present this paper?
Ivanov Aleksey, I suppose.
Good afternoon. Do you hear us?
Of course.
And
we can see the screen.
Okay. The name of our topic is, I mentioned, development of the models of methods for the automatic control of the manipulator drives of a mobile weeding robot with a parallel serial structure. Slide 2. When calculating vegetables and cucurbits, one of the time-consuming and energy-consuming tillage operations is weeding, which is usually carried out by cultivation. Chemical methods of weed control have recently been used less frequently for environmental and economic reasons. When growing vegetables in greenhouses, manual labor is used overwhelmingly. With mechanical destruction of weeds, the cultivator's working bodies processes only the inputs. The introduction of highly efficient means of mechanization of robotic systems for the cultivation of crops, such as robotic weeding machines, will reduce manual labor and injury to crops. Slide 3. Slide 3 shows the current state of the issue in Russia. Despite significant progress in the development of agricultural technologies and equipment, there is still a lot of manual labor in this industry. Slide 4. Britain, Germany, Switzerland, Australia, France are actively developing the introduction of robots for the destruction of weeds. Slide 4 shows robots Bunny Rob, Eva, Ripa, Dina, which are designed to destroy weeds. Slide 5. The Volgograd Agrarian University has developed a weeding robot which consists of a frame 1, steered wheels 2, a control and navigation system with instrumentation 3, a power supply system 4, and a vision sensor 7. The movement mechanism of the working body of the weeding robot figure 2 is a flat mechanism of parallel sequential structure with 3 degrees of freedom. To move the working body 8 in the horizontal plane, 3 linear actuators 5 are used. In the vertical linear actuator 6, the rotation of the working body is carried out using an electromotor 9. Slide 6. The technological process of weeding is carried out as follows. With the help of the control and navigation system, the weeding robot enters the rows of plants. With the help of a computer vision system, the coordinates of the location of weeds in a row are determined. In automatic mode, the working body of the manipulator moves to the weed, where the cutting tool of the working body is above the weed. It moves vertically, cutting the weeds and loosening the soil next to it. Slide 7. For the implementation of the described technology, it is necessary to develop algorithm for the formation of a system for the weeding robot working body movement control. In this case, the control system must ensure the movement of the working body to a given point in the working area with the necessary accuracy. The movement of the manipulator in the horizontal plane is considered. The problem is solved in 2 stages. First, the positioning problem is solved for the given final coordinates of the mounting point of the vertical actuator. It's required to find the generalized coordinates of the manipulator. At the second stage, it is necessary to determine the laws of the change in the generalized coordinates of the manipulator when moving at the attach point of the working body from the initial to the vicinity of the design point. As control parameters, we take the acceleration of changes in the generalized coordinates. Slide 8. Manipulator positioning. The design of the manipulator provides holonomic connections between the coordinates of the point 04, x4 and y4, the length of the actuating links and geometric parameters of a manipulator. The configuration of the manipulator is determined from the minimum condition of the quadratic function, the criterion of the generalized energy, with inequality constraints, equitation 2. Slide 9. The Lagrange objective function has the form equitation 3. The necessary conditions for the extremum of function 3 are written in the form equation 4. Since the Lagrange function 3 is convex and factors 2.1 when not presented at the picture, the necessary conditions 4 and 5 are sufficient. Stabilization of the slide 10. Stabilization of the given position of the manipulator, second stage. Since the manipulator has great rigidity, the Cartesian coordinates of the actuator attachment point with the working body are determined through the length of the actuating links with great accuracy according to equation 6. At the initial time, the configuration of the manipulator is determined by the length of the executive links. The method of control system synthesis for the laws of changing the length of the executive links is described below. We assume that the trajectory of motion, deviations from the final state of the executive links, change is accordance with the solution of differential equation 7. Differential equations 8 corresponding to the laws of the formation of the driving actions of the actuators determined by equation 7. Slide 11. Under initial conditions describing the state of the manipulator at t0 equal 0 equations 9, the general solution of the equation 8 has the form equation 10. The integration constants are found from 8 taking into account 9. The coefficients of equations 8 are determined through the roots of the characteristic equation. Slide 12. The law of changing the length of the actuating links 10 is software. To construct a feedback control law, it's necessary to calculate the required acceleration from the current values of the generalized coordinates and velocities equation 12. Figure 9 shows a block diagram of the control system. Slide 13. Control system structure. Functionally, the control system can be divided into two levels. The upper level provides general traffic planning, GPS receiver processing and navigation, communication with remote control and telemetry via Wi-Fi protocol, implements and vision system. The low level of the control system provides direct control of the actuators of the reading robot. Figure 10 shows a functional diagram of the control system. Slide 14. Control of actuators is based on the identical 4-channel drive controllers. Each of the controllers is built on the microchip PIC16F73 microcontrollers, which have two PYM generators for motor control. Feedback is implemented in 4 Vega HCTL 2017 microcircuit counters for optical radiator encoders. In addition, each controller has 8 GPIO lines, general purpose digital input-output, and 5 analog input lines. With their help, the feedback of the drive is realized on potentiometers. Slide 15. Slide 15 shows the drive control unit. Slide 16. The sensor system consists of two main components. One is rigidly attached to the actuators, and the second, which performs most of the functions of global navigation and spatial orientation, as well as technical vision, is connected to the top-level control unit. Slide 17. Following the two-level organization of the hardware, the software of the reading robot includes function libraries for working with lower-level modules and upper-level client programs. Libraries are functioning for working with controllers provide transmission of control commands and interrogation of navigation data and position senses of the manipulator. Slide 18. When describing the mathematical model of the manipulator, the length of the executive links Q1 equal 11, Q2 equal 12, Q3 equal 13, and the rotation angles of the electric cylinders relative to the movable coordinate axis Q4 equal A2, Q5 equal A3 are taken as generalized coordinates. The coordinates are independent holonomic connections are superposed on the coordinates Q2 equal 12, Q3 equal 3, Q4 equal A2, Q5 equal A3, equation 13, 14. The equation of the dynamics of the movement of the reading robot are formed using the Lagrange equations with indefinite factors. 15. Slide 19. The slide shows the kinetic energy equation of the manipulator. Slide 2021. Using the expression of kinetic energy and the equation of the holonomic relation 1314, we obtain 5 differential equations describing the reading robot's mechanism dynamics. Slide 22. In the figures 1314 shows the results of calculations of the numerical example of the implementation of the control algorithm. From the graphic figure 1314, it is seen that during T equal 0.5 as the capture device is stabilized in the given position. Deviations from the set position don't exceed 0.1%, and the speeds and accelerations are practically equal to 0. The trajectory of the point slightly differs from a straight line. If the generalized coordinates of the manipulator divide from the program path, it makes no sense to stabilize them on the original program path, since at each current point another program path is constructed that satisfies the same final conditions. And figure 14 presents the laws of change in driving forces obtained as a result of solving equation 16 from 16 up to 20. Slide 23. As a result, the problem of positioning the manipulator and the problem of weak terminal control are solved. The program path is corrected in such a way that each moment of time it passes through the current position of the working body. Over time, the working body falls into the final region of the target point. An algorithm for generating control voltages is formed taking into account the kinematic parameters for the manipulator in all degrees of freedom. The mathematical modeling showed that the proposed algorithm allows you to implement capturing along the program path with an error of no more 1%. The algorithm also functions well in the presence of initial perturbations. Thanks for your attention.
Thank you very much for this nice presentation. Do we, any chance we have any comments from the virtual audience? All right.
I have a question, if you don't mind.
Of course.
What types, what type of regulators do you use?
Yes, we understand the question. In this reading robot, we use PEAT regulators.
You said that the positional accuracy for your robot within the mathematical simulation was above 1%. So, what is the position accuracy in the real robot? Afterwards.
If we use the robot, if we speak about accuracy, about up to 10%.
After 10. Okay, thank you.
Any questions?
All right. Any other questions? All right. Thank you very much for the
Thank you
presentation.
for your attention.